All right, so what you should have gotten out of that POGL that we did the other day on free energy is that there are three things that you have to consider when figuring out whether a reaction is spontaneous or not. So spontaneous reactions follow the following pattern. They have a tendency to lose energy, because that's what happens in the universe, right? Or they have a tendency to become more disorganized. And so we talked about some examples where, all right, so by and large, exothermic reactions we predict are going to be spontaneous, but there are still a couple of exceptions. We have a couple of endothermic reactions that happen on their own. So what gives? Like, why is that spontaneous? And then we have a bunch of reactions that are spontaneous when they gain entropy, but then there's some reactions that they lose entropy, but they appear to be spontaneous anyways. So we figured out that there had to be a temperature dependence on this as well. So spontaneous reactions, really, you can't just look at each of these individual things on its own. You have to look at them all together. So number one, you have to look at what is the change in enthalpy. Number two, what is your change in entropy? And number three, what temperature is the reaction occurring? So all three together is really what you have to look at when determining whether a reaction is going to be spontaneous. And the way that you look at all three of these things together is by calculating something that we call Gibbs free energy. And the equation for Gibbs free energy is delta G is equal to delta H minus T delta S. And that equation was at the back end of the POGL. Essentially, what you're going to do is, you had some problems in the book on page 836 to do for homework, where they asked you to calculate this. Essentially, you calculated delta H from the table in the back of the book, you calculated delta S from the table in the back of the book, and you just substitute them into here. And what you really need to know is this punchline, is that when delta G is equal to 0, your reaction's at equilibrium. When the delta G, when the value for Gibbs free energy is positive, that reaction is not spontaneous. When delta G is negative, that's when your reaction is spontaneous, after you've considered all three of these factors up here. All right, and so this is really, I'm going to highlight this, because this is really what you need to know for the AP exam, is this business about delta G being positive and delta G being negative. All right. So one of the things that I should forewarn you about when it comes to things calculating delta H and delta S out of the back of the book is that if you look at the values that are tabulated for you in Appendix C, delta H is given to you in kilojoules per mole. However, delta S is given to you in joules per mole Kelvin. All right, well, can we subtract joules from kilojoules? The answer is no. So whenever you go and substitute any of the numbers that you calculate in the back of the book into this formula, you either have to make both of these joules or both of these kilojoules before you proceed. All right? What about temperature? What unit should temperature be in? Kelvin. You also have to remember that temperature has to be in Kelvin so that your units are consistent between temperature and delta S. Okay? The math here is simple. The formula is easy. Where students mess up time and time again is on these two things. Number one, making sure that the temperature is in Kelvin. Number two, making sure that either you have joules and joules or kilojoules and kilojoules. All right? It's consistency for the units. And the reason why students usually mess up with this is because when they're plugging numbers into these formulas, they just plug in the numbers, not the unit. And so when you get a little complacent that way, when you're not writing down the units, and you very quickly forget that the units are given to you in inconsistent values. All right? So you just want to be sure that you're aware of that trap. All right, so you had some homework to do on page 836. You had to do questions 39 to 41, 45, 49, 53 to 57, 61 to 65. All right, so I'm taking requests. Which ones would you like me to go over real quick before we move on with our lecture today? I can tell you that First period asked for 53. I'd like to do that one with you because that's a pretty characteristic type of question that they're going to ask on the AP exam. But if you have other ones that you'd like me to do, I'd be more than happy to do them. Do you find this easy to do? Yeah? Okay, well, first period, it wasn't because it was easy to do, it's just because they didn't do it. That's why I didn't have too many requests. Some were able to do it. I want to go over 53, though, with you, just to make sure that you grasp it. So question 53, let's take a look at it on page 836, and then we'll move on from this particular point. This is a pretty classic question that really does represent both the way they would phrase things on the AP exam and both on the multiple choice and the FRQ. And I know that this is not going to zoom in for me on the video, but let's see what we can make of it. Yeah, that's not helping, is it? Can you read that? Right there. Can you sort of make it out? Right there. Alright, so it says for a certain chemical reaction, delta H is negative 35.4 kilojoules, delta S is negative 85.5 joules per Kelvin. And then they ask, A, is the reaction exothermic or endothermic? Alright, that's a pretty straightforward thing. B, does the reaction lead to an increase or decrease in the randomness or disorder of the system? C, calculate delta G for the reaction at 298 Kelvin. And then D, is the reaction spontaneous at 298 Kelvin under standard conditions? Alright, so that's what they're asking for. Let me move the book and let me write down some of these things on paper so that you can see how it's done. Yeah, that's not much better, but let's see what we can do. Alright, so they're telling me delta H is negative 35.4 kilojoules. They tell me delta S is negative 85.5 joules per Kelvin. Alright, so first things first. Is it exo or endothermic? Why? Delta H is negative. Alright. Okay, then B. Are we becoming more or less disorganized? Okay, yes, I didn't ask if we were becoming more organized. I asked if we were becoming more or less disorganized. What is does S represent organization or disorder? Disorder. So are we gaining disorder or losing disorder? We're losing disorder. Why? Because delta S is negative. You lose disorder when delta S is negative. You gain disorder when delta S is positive. Alright? Let me hide this at the bottom here. Can I move this so that yeah, I can. Okay, then finally see what's delta G. Alright, well delta G is equal to delta H minus T delta S. That's too much. One day I'll finally get this set up right. Yeah, this is not working at all. Yeah, let me rip the paper up and fold it. Okay. All right. So let's go ahead and substitute the numbers that I'm given in the question. All right. So delta H is negative 35.4, and I'm not going to be lazy. Let me put the unit there just to remind myself of what I'm doing. Minus the temperature. All right. What did they tell me the temperature was for this? 298 Kelvin. Okay, great. They gave it to me in Kelvin already. That's fabulous. All right, and then delta S is negative 85.5 joules per Kelvin. All right, but you'll notice, right, that this is kilojoules, this is joules. That's inconsistent. All right, so either I change both to kilojoules or I change both to joules. I prefer, because of the order of magnitude that we're talking about, to just go ahead and change it to kilojoules, because usually these things are usually in that size scale. So the way that you change this to kilojoules is divide by 1,000. All right. Remember, it's division, not multiplication. All right, so then it's just a matter of putting this in my calculator. I had my calculator here. Someone borrowed it and didn't put it back where it belongs. Oh. Okay, so let's take a look here. Negative 35.4 minus 298 times 85.5 and negative 85.5 divided by 1,000. Oh, okay. So the answer that I get is negative 9.92 kilojoules. All right. And then question D then asks, well, based on that answer, is your reaction going to be spontaneous or not? And your guess is? It's spontaneous. Why? Because that delta G is negative. So what we mean when the reaction, when we say that it's spontaneous, is that it's spontaneous in the forward direction. All right? The reverse direction is going to be not spontaneous. All right? Okay, so the bulk of the homework was just, either calculating delta S out of the charts in the back of the book, or calculating delta G from delta H and delta S and T, and figure out whether things were spontaneous or not. The math was really not all that challenging. So if you still have issues with this homework assignment, I'll be available tomorrow afternoon in the event that you need some help. But really, it's more tedious than anything else, because you had to flip back and forth to that table in Appendix C and pick numbers off and go from that particular thing. Okay? So there's no more questions about this? All right, so if there's no more questions about this, then we'll proceed with what we're going to do today. All right, so let me reset this camera. So what we need to spend a little bit of time talking about first is how free energy is related to equilibrium. And you really don't have to copy, if you want to keep yourself entertained and you want to copy some of this down, you can, but you don't. These PowerPoints are actually kind of wordy, because I stole them from somebody, and I'm usually not in the habit of writing wordy PowerPoints. That's bad form in PowerPoint world. But I will make this available to you so you have it. But if you want to keep yourself entertained and keep yourself from dozing off, you might want to write the gist of these PowerPoints. So first things first, really what you need is this table, right? How is Gibbs free energy related to K, the equilibrium constant? Well, when Gibbs free energy is equal to 0, our system's at equilibrium. And what did you learn about the K value for a system at equilibrium? What's it equal to? 1. It's equal to 1. All right. This is something that they do on the AP exam a lot. Okay. You see how it says delta G is less than 0? What's the synonymous way of saying that? No, it's less than 0. What's another way of saying that? It's negative, right? Delta G is a negative value. They'll phrase it in either way on the AP exam. You just have to know that this means also that it's negative. So what do we learn about delta G being negative from that Pogel? That's spontaneous. What you need to understand is that we're talking about it's being spontaneous in the forward direction. What did you learn about K values for reactions that were spontaneous in the forward direction? They were greater than 1, right? What about delta G is greater than 0? What's the synonymous way of saying that? That delta G is positive, all right? What does a positive delta G tell you? It's not spontaneous. And when we say it's not spontaneous, we mean it to say in the forward direction. All right, so reactions that are not spontaneous in the forward direction are going to have what kind of K values? K values, they're going to be small K values, right, if they're not proceeding from left to right. So they're going to have K values less than 1. All right. Now, I want you to notice something. I don't know if you noticed this in the back of the book, but there's always a superscripted 0 for delta H, for delta S, and delta G. All right. The superscripted 0 means that you're calculating the standard change in Gibbs free energy. And by standard what we mean to say is that that reaction, the delta H and delta S, were measured very specifically under standard concentrations. So that means that any reactant that you used was supplied at a 1 molar concentration. If it was a gas, that gas was provided to you at a 1 atmosphere concentration. All right. There's a formula that allows us to calculate the equilibrium constant K for an equation knowing delta G. It's right here. It's delta G naught is equal to negative RT ln K. When you calculate delta G from the back of the book, you're calculating delta G naught, the standard one, because all those numbers were measured under standard conditions. Okay. Now, recognize R? What is it? It's the gas constant, except for we learned 2 versions of R. One was 0.0821 and the other one was 8.31. In this case, we're going to use the 8.31 version. Why? Because that's in joules. We're talking about energy. Okay? All right, so let's do a little sample problem here. It's kind of blurry. I'll read it to you, but I want you to see how this math is done. All right? It says, determine the standard free energy change for the formation of 1 mole of ammonia from nitrogen and hydrogen, and use this value to calculate the equilibrium constant for this reaction at 25 degrees Celsius. So essentially they want me to calculate delta G using Appendix C. And then take that value and figure out what K is at 25 degrees Celsius. All right? So let's do it together. All right? So let's start with writing a reaction. Okay, so in this particular reaction, I'm taking nitrogen and hydrogen and making ammonia out of it. Does anyone have any issues with my equation? It's not balanced. Okay, so what do? What do I need? Thank you, Omar. Great. 3 in front of the H2, 2 in front of NH3. All right, so I flipped my book to Appendix C because I want you to see the kind of information you have. All right, so in Appendix C, you're given all these substances. You're given 3 columns, right? So one is delta H. One is the Gibbs free energy of formation. One is delta S. So I'm going to use this column here to figure out delta G for that reaction from the delta G of the formation of those compounds from elements. All right? So how do you do that? How do you use this table? How did we use this table before to figure out the delta H of a reaction or the delta S of a reaction? Didn't we do the sum of the products minus the sum of the reactants, right? Well, we can do the same thing for delta G using that column. All right? So I'm going to look up the value for delta G for N2. All right? And it has to be in the same state that it was given to me in the equation. And these two things, this equation, this reaction is called the Haber process. It's all gases that I'm playing with here. All right, so if I look up delta G, so that second column on the table for nitrogen gas, the value is 0. If I look up the value for hydrogen, take a guess. What do you think the value is going to be? We learned it's going to be 0. Why? Because elements in their most stable form have values of 0 across the board for everything, right? And then if we look up NH3 for a gas, the value is negative 16.66. All right, now, do the coefficients matter? Do they matter? Yeah, because these numbers are in kilojoules per mole. I don't have 1 mole here. How many moles do I actually have? 2. All right, so the sum of the products is going to be 1 times 0, that's reactants, plus 3 times 0, right? So what is the sum of the reactants? 0. Let me rewrite this down here. So sum of products minus sum of the reactants. So we're subtracting 0 from the sum of the products. What's the sum of the products? Is going to be 2 times negative 16.66. So what is that? Negative 33.32 kilojoules. The mole unit has canceled out because I multiplied by 2. This was 2 moles times that many kilojoules per mole. So what is my delta G for this reaction? It's negative 33.32 kilojoules. All right? Now they want me to figure out the value for the equilibrium constant. So because this is negative, what does that tell you about the reaction? Let's make some predictions here. It's spontaneous. So what does that tell you about K? What do you predict? It's going to be greater than 1 because his reaction's proceeding from left to right. We're going towards products, right? We're product favored. All right, so let's actually figure out what that value is. So what was the equation? What was the equation? I have to flip the paper. Delta G is equal to negative RT ln K. All right, so let's go ahead and substitute. Delta G is negative 33.32 kilojoules is equal to negative 8.314 joules per mole. Oh, man. What's wrong with this picture? We have inconsistent units again. So let me just go ahead and divide that by 1,000 to change it to kilojoules, right? Times the temperature. The word problem told me it was 25 degrees Celsius. Do I put in a 25 here? No, why not? It has to be in Kelvin. I'll put 298 Kelvin instead. Times the natural log of K. All right, so how do I isolate ln of K? What would we do? We would do 33.32 divided by this product here on the right-hand side. I'm going to do it in my calculator, and then I want you guys to confirm for me if that's the answer that you get. I get 13.45. Is that what you get? And again, this is the capital K, the equilibrium constant, not little k, the rate constant. Right? How do you get K alone now? What do you do? How do I get rid of the ln business? What's the base of ln? E. So then to get K, you do what? E to the 13.45 power. And then the answer that I get is 6.93 times 10 to the 5th. Is that bigger than 1? Yeah? That's significantly bigger than 1, so our prediction was correct. Okay? All right, well, that's how you can get K from delta G. Now, would you see a question like this on the AP exam? Sure. This might be part E or F of a free response question. They would make you go through that whole process initially of, is this exothermic, endothermic, spontaneous, not spontaneous? That would be parts A, B, C, and D that you would have to answer before you got this far along. Okay? Do you have to memorize this equation? No, it's on the reference sheet. You just really need to focus on how to use it. And really, the key is remembering to keep your units consistent before you divide or add and subtract, and just making sure that everything's in the same consistent unit. All right. Okay, let's look at this next part. Here's another equation that you need, and this is the last slide, and we're done with this chapter on thermochemistry. All right, so what if delta G is not measured under standard conditions or standard concentrations? Can you figure out? Can you still use that table in the back of the book to figure out what Gibbs free energy is going to be if you use totally different concentrations other than 1 atmosphere? Yeah, you sure can. You use this equation instead. All right, so again, the little superscript of 0 means that that's under standard conditions. That's what you get out of the back of the book. This is what the value would be under non-standard conditions. So the formula is delta G is equal to delta G naught plus RT ln a Q. You guys remember what Q was? What's Q? What's that? Is that the reaction quotient? Is Q calculated the same way as K is with the same mass action expression, but instead you use the initial line from the Rice chart? Yep. All right, so let's do a sample problem. It says calculate delta G at 298 for the following reaction if the initial mixture consists of 1 atmosphere N2, 3 atmosphere H2, and 0.5 atmosphere NH3. It's the same reaction that we just did. It's ammonia being manufactured from nitrogen and hydrogen. And we just calculated from the back of the book the standard Gibbs free energy if we had used 1 atmosphere of each thing in order to measure this reaction, right? And we figured out that delta G naught was negative 33.32 kilojoules. Okay. This came straight out of the back of the book, doing the sum of the products minus the sum of the reactants. All right, well, what if we wanted to figure out what delta G is under non-standard conditions? Then all you simply do is you take that delta G that you get out of the back of the book from those tables that have already been measured by somebody else, and you add a correction factor. That's what this plus RT ln Q is. It's a correction factor. All right. All right, so let's do it. Before I actually substitute any real numbers, though, we're going to play a little bit of alphabet soup here. I'm going to rewrite the equation, but instead of writing Q, let's go ahead and write the mass action expression for this reaction. All right, so what is the mass action for this reaction? What goes in the numerator? Change in it. These are gases, right? So I shouldn't be using square brackets. I should be using pressure instead, right? Pressure of NH3 squared over pressure of nitrogen to the first power, pressure of hydrogen to which power? Third. Okay, fun. All right, well, what was delta G? We calculated it was negative 33.32, and again, don't get lazy on me, put the units in so you realize whether you're being consistent or not. All right, what's R? 8.314 joules, per mole Kelvin. That's inconsistent, right? So divide by 1,000. What's the temperature? In the question they told me the temperature was 298 Kelvin. Natural log, all right, the pressure of ammonia. How much ammonia did they use? 0.50 atm, quantity squared, over 1.0 to the first power, 3.0 cubed. All right, so do you guys have your calculators? Let's see if you can compute an answer off of that. It's a little messy, but it's doable. I don't know if I'm getting the right thing, but I get negative 44.9. So one of you guys confirm or discredit that? That's what you got? Okay, great. So that's really what your delta G is going to be under these new conditions. Okay? So that's really all that you do. So look at what happened. Our delta G went from negative 33 to negative 44.9. What's so significant about that? Is it becoming more spontaneous? So under these new concentrations, Am I producing more product than I would have if I had used standard concentrations? Yeah, you are. Okay. All right. Are we good with this? Okay, great. Let me pause the video there. I'm going to actually do this in 2 segments because of the fact that I'd like to keep thermochemistry a little separate from electrochem. Okay, you can stop recording now.